Let me quickly remind you what we've done in the previous class. We basically discussed RC circuits, right? And there are two types of them. So you can first charge a capacitor. So charging case, we discussed it, I think, diligently. All right, and derived all the functions describing how charge and charge in the capacitor, current through the resistor, and potential differences through elements are changing in time. So we derived that all right? And then we also just glance through, and I emphasize on major points about discharging case when the capacitor is full and you discharge it through a resistor, right? And current function which describe current is exactly the same in both cases, right? Charging and discharging. It decays exponentially. How charge changes in the capacitor with time, of course, different, because in the first situation, charge inside of the capacitor is growing, right? But in the second case, in the discharging situation, of course, it decays and decays exponentially, right? And then, of course, you can easily also get the potential differences across elements, right? Using either Ohm's law or the definition of capacitance, right? I showed to you yesterday. So now, as a result, so now let's apply that for problem 35. So 2835, and in this situation, we're going to discharge a capacitor. So it's a RC discharging. Okay, so what is given? We have capacitor and, okay, of course, capacitor at the initial moment of time is full. Okay, or let's say there is some amount of charge. And that charge is given, Q naught. Right. Capacitance is given, the amount of charge in the capacitor is given at the initial moment of time, right, at t equals 0, and it will be discharged through 1 kilo ohm resistor. Okay, let me quickly draw the circuit. So just to, so this is our capacitor, and then of course the resistor. So that's our circuit. So C, R, and so what needs to be found? What needs to be found? Let me write. So we need to find some moment of time. Let me label it as T1. When the amount of charge in the capacitor is or reaches 10 microsecond. Wait, microcoulombs, damn it. It's still morning, it's still 8 a.m. So I can blame that. So pretty much we can ask, so how long does it take to reduce the capacitor's charge to 10 microcoulombs? Basically by a factor of 2, because initial charge is 20 microcoulombs, and the amount of charge at that moment of time, at this moment of time, will be smaller by a factor of 2. So T1, when charge, let me label it as Q at T1, and I can also label it as Q1 for simplicity, and it will be equal to 10 microcoulombs. So that's the situation. And now, you know what? Before even I start writing any functions, write any equations, let me draw a plot, right, which we drew yesterday. Right? So let me plot how charge, in order to understand what needs to be found. So this is charge, this is time, right? For a discharging situation, what happens with the current, I mean with the charge in the capacitor? It decays exponentially, something like this, right? And what needs to be found? This moment of time. So this is, okay, this is Q naught. This will be Q1, halfway down, right? And so we need to find this moment of time, T1, when charge is reduced by a factor of 2. So that's what we need, okay, on a plot. And again, so what can be done? So we know we know the function which describes this plot. So we just need to grab that function. Of course, guys, be careful which functions you use, because I warned you in the yesterday in the previous class that some students just grab the wrong functions and applied them for the wrong situation. Right? So in this case, in the discharging, of course, capacitor charge inside of the capacitor is described by this function. Q equals Q naught times e to the power of minus t divided by tau. Right? Okay, let me even frame it, because yeah, it's beginning, right? So equation which, okay, function which describe how charge changes. And usually in your homework, of course, you will see like 3 problems, I think, about RC circuits, right? And most of the problems are of these 2 types. First one, for example, time is given and you need to find charge, or maybe current, or potential difference, right? It depends on the problem. Or something in reverse. The amount of charge or current or potential difference will be given, and you need to find time when that happens. And that's what we have here, right? So we have information about the charge at a certain moment. So we have information about the charge, and we need to find that moment of time. So basically, we just need to use this equation. But before we start using this equation, what needs to be found? Because right now there are 2 unknowns in this function. We know the time, but we also don't know the RC time constant. But RC time constant tau, it's basically an intrinsic parameter. If you know everything about the circuit, right? If you build the circuit, so you can calculate that easily, because time constant is just a product of resistance and capacitance. Right? So before we start actually massaging this function, so let's first find tau, RC time constant. And again, you remember, it's an important parameter which tells us basically how fast okay, capacitor gets charged or discharged, right? The shorter tau, the faster it happens. It's okay. And you know what? Probably in 10-15 minutes, I will show actually, right? So that product of R and C gives us units of time. But I will do it later. So what do we have? R 1 kilo ohm. So 1 times 10 to the power of 3 ohms times 2, where is C? Okay, 10 microfarads. Micro 10 to the power minus 6 farad. Right. Okay, so the answer will be -3, -2. So it's a 10 milliseconds or 0.01 seconds. Okay, let me check. Yeah, 10 milliseconds or 0.01 seconds. So now once we know time constant, we can actually find T1. Okay, so now I will just apply this equation, this function for this particular point. So it will be Q at T1. Okay, for simplicity, I introduce this Q1 because it's too much to write. So, and it is equal to Q naught and e to the power of minus T1 divided by tau. So now, yeah, we have only one unknown, and we need to solve it. For that, it's a T1. So what do we have to do? Okay, let me do it step by step. Of course, first this factor I will move to the left-hand side in the denominator, right? So it will be Q1 divided by Q naught equals to e to the power of minus T1 over tau. Then, guys, what do we have to do with this equation in order to drop this power? Okay, by dropping this power, I mean to the level of E. We need to apply natural log, right, on both sides. Natural log to this side and natural log of that side, because natural log of okay, let me check. There's some activity in the chat. I just noticed. Yeah, taking the natural log, of course. Yeah, Cindy just typed it. Yeah, so we will get natural log of Q1 over Q naught equals to minus T1 over tau. Right, so that will be if you apply natural log to both sides. And so that's our unknown, so let's just solve it. So it will be T1 equals to minus tau times natural log of this ratio Q1 over Q naught. Okay, so we can call it basically the answer, but you know what? My another minor compulsion, whenever I have a minus in front of the expression like this, I don't know, it just makes me feel uncomfortable, right? I want to hide those minuses all the time, right? Following probably advices of psychologists, be on a positive side, don't have negative attitude. So let's remove this minus. And so how can we hide that? You remember that property of natural log of x to the power of minus 1 equals to minus natural log of x. So it means that minus this minus, I can move here to the power of minus 2. Oh, minus 1, sorry, minus 1. So it means that I can just flip this ratio. Right. Okay, so finally it will be T1 equals to tau times natural log of Q naught over Q1. Okay, so I would claim this as the algebraic answer. Now, of course, we can plug numbers. I'm not going to do it. Okay, maybe partially. So it will be 0.01 seconds. That's tau. And then natural log of what? Charge is reduced by a factor of 2, right? Initial charge 20, final 10. So it will be natural log of 2. So if you take natural log of 2, it will be, you will end up with what? 6.9 in units in milliseconds. 6.9 milliseconds. So now, let's see, does it make sense? Let's just compare, for example, with our time constant. Does it make sense that this time T1 is smaller than time constant, tau, RC time constant? Yeah, it makes sense because what happens at the time constant tau? The charge is reduced, or gets reduced to 37% of its maximum value. So it will be 0.37 of Q naught. So time constant will be somewhere here. Let me tau, right? And this will be, okay, let me do it like this. This will be 0.37 of Q naught. But Q1 is 0.5 Q naught, right? So it makes sense, of course, that T1 must be smaller than tau. Right? Yeah, it makes sense. 10 microseconds, milliseconds, and here 6.9 milliseconds. So something like this. And homework problems will be of this level, but sometimes it can be just time is given and you need to find the value of whatever. But you know what? I decided to add 2 additional questions. Yeah, the problem is over, but I added 2 additional questions. All right, so I will put a bullet, additional, questions. And I ask, what about potential difference? For example, like across the capacitor, because potential differences are going to be the same, right? In absolute value. And also, how can we find current, right? So let's say we want to know more about this, right? So let's first find potential difference. So delta V across the capacitor. So how can that be done? We discussed in the previous class, right? Just from the definition of capacitance, C equals Q over delta V. But now we need to find delta V, so it will be Q over C. Right. So Q, again, is a function of time. It means that our delta V is also the function of time. Right. So divided by C. And you see now I'm finding the functions. I just want to write down a function, how potential difference changes with time. Of course, if you're interested at the value of the potential difference at this particular moment of time, T1, yeah, plug it, find it. Once you know the function, you know everything about that quantity, right? Just it's a question of plugging and calculating. All right, okay, so Q is here, and we've already found tau, so it will be Q naught e to the power of minus t over tau divided by C, right? Q naught and C are given. Q naught, you see, it's 20 microcoulombs divided by C is 10 microfarad, and e to the power of minus t over tau. So it will be 2 volts. That's the maximum potential difference. And then it will decay exponentially. So that's how potential difference across capacitor changes. And of course, it will be a similar story across the resistor, because there is nothing else in this loop. So now next, what current? Yeah, I want to find current. So that's the first additional question. And now the second, what about current? And of course, current will be also a function of time. Now, which formula do we have to use? And you need to recall the previous class. You remember the relationship between a current and the charge inside of the capacitor for the charging situation. This is discharging for charging situation. For charging, I was equal to dq over dt, basically derivative of this q with respect to time, but with plus. But for a discharging case, the relationship was minus, right? You remember I spent like 5 minutes, I digress, and spent 5 minutes like justifying plus sign for charging situation. And then I said it will be very similar, and if you want to look, you can look at my slides, can be done for a discharging case. For discharging, there is a minus, don't forget, there is a minus. Minus dq over dt. And of course, q is a function of time. We have to differentiate function, not a particular value of charge at some particular moment of time. Right. Okay, so it will be minus d over dt. And of course, you differentiate this function. Let's say it's a q naught e to the power of minus t over tau. Right. So minus q naught stays in front. Then you need to differentiate this function e to the power. So it will give us minus 1 over tau, right? And exponential function stays. That's the beauty of exponential function. It doesn't matter what you do with it. Differentiate, integrate, every time it will pop up at the end, giving some additional factors in front, but every time it will survive, right? Amazing function, right? But anyway, minus and minus give us plus, and then q naught and tau are given, right? So q naught is 20 microcoulombs, and divided by tau, tau is 10 milliseconds. And e to the power of minus t over tau. Right. Okay, let me write it lower. So it will be 2 milliamps. Yeah, here 10 to the power of minus 6 micro, here 10 to the power of minus 3 milli. So of course, as a result of the ratio, you will get milliamps, and 2 milliamps times e to the power of minus t over tau. Right. So that's how current changes. And again, if you're interested in the value of the current at this particular moment of time, so you found time, plug it and calculate what will be the current, value of the current at that moment. And the same about the potential difference. So pretty much, yeah, we exhausted. We found almost everything that we can about this particular circuit. The next one is easier, right? So it's the same chapter 28, but now problem 33. Usually I discuss also one conceptual question in class, but this time I decided to skip. I will discuss it in the problem only. So we have this circuit. Okay, let me draw it here. So first we have two resistors, and then we have one capacitor, and here there is a second. Okay, I did my best. And what we have? So C1 is 2 microfarads. C2 also 2 microfarads. And resistors are given. So R1 R1 equals to 1 kilo ohms, and R2 also equals 1 kilo ohm. Right. So effectively, what do we have here? What kind of circuit? It's a discharging situation, the same as here. But now, instead of one capacitor and one resistor, right? So because everything that we've derived, we derived for this simplest possible when you have one capacitor, one resistor. Even when we were charging capacitor, of course, we had one capacitor. But now, wow, it's something, we have two capacitors, and the charge is being dumped through two resistors. So how can we find, for example, RC time constant of this? It will still discharge the total charge that we have here somehow through those resistors. So how can we find time constant? So let me first emphasize that this is still discharging, right? Because it's important, because yeah, as I told you, sometimes students just use the wrong expressions for the wrong situation. So RC, and let me write discharging. Right. So, and as I said, we need to find RC time constant. And so now, since we know okay, reasonably a lot about the simple circuits, now we can look at this and we can say, so what? So we have two capacitors and two resistors, but we can easily simplify it using equivalent values, equivalent resistance, resistor, and an equivalent capacitor. So we can easily redraw this picture into something like this, right? So we have R equivalent and C equivalent. And how to find this R equivalent, C equivalent? We know, right? It's a piece of cake. And again, we see that these two capacitors obviously connected in parallel because potential differences must be the same, right? Are the same, potential differences are the same. And those two resistors connected in series because currents through them are the same. Right? So now it's very simple. So which way I wrote? Oh no, I will just write first definition. Tau equals to RC, frame it, right? And then of course, yes, so I should add equivalent, right? So now we need to find those equivalent values. And on purpose, I picked the easiest for the class, right? So that we wouldn't waste much time, right? But of course, for the homework, will be slightly more complicated. Actually, you will have like 3 capacitors and 3 resistors. But again, it's just extra of additional work, but conceptually, it's basically the same. So R equivalent equals to R1 plus R2, and that will be, of course, 2 kilo ohms. And then C equivalent. Also, you remember when capacitors connected in parallel, we need to just add their values in order to find equivalent capacitance. So in this case, again, C1 plus C2. So it will be 4 microfarads. Okay, so now of course we can find the time constant. So it will be 2 times 10 to the power of minus 3 ohms times 4 times 10 to the power minus 6 farads. Again, micro, negative 6. But I'm sure that at this point you already remember that. So that will be 8 milliseconds. Yeah. Negative 6. Oi. Nanoseconds? No. Hold it. Kilo. And you guys not screaming at me so far, right? Sitting quietly, right? So I wrote kilo, but wrote negative 3 because I don't remember such a short time constant, right? It's something is fishy. No, there shouldn't be a minus over here. It should be plus. We have kilo ohms, right? Not milliohms. That's too much, too little. Right? So yeah, now it sounds good. So 8 milliseconds, 8 milliseconds. So you see, problems about RC circuits, they're not complicated, right? So you just usually play with function, right? And finding RC time constant. Right? Yeah, and of course you know RC circuits are used a lot in filtering noise, right, and so far and so on. Actually, I remember in my case, I was doing my sort of final project before my PhD defense. No, before, way before, right? All right, and we are applying square pulses to the laser, our quantum cascade laser, and for whatever reasons, when you look at the output power, okay, laser signal, it was sort of bistable all the time. Signal was jumping, right? Power larger, power smaller, larger, smaller. And of course, in applications, it's it's impossible to do any serious work if your power is jumping like that. And then we noticed that if you make your pulse smooth, right? So if you don't have a square pulses, right? Then that bistability disappeared. So I built some calculated RC time constant, the one which give me the best results, right? And then put it between the power supply, right, and my laser, right? So this small box with RC circuit, which made my pulses smooth. So instead of square pulses, we had a sort of short voltage was increasing for some finite period of time, and then it decayed over a finite period of time, and it helped the result that bistability disappeared, right? And then we wrote a few papers and we used those pulses to drive our lasers. So it's a quite common situation, right, where RC circuits are used, right? As I said, filtering noise. Okay, and so you see it's not complicated. And the last thing before we move to the new world, let me just quickly show that actually RC, product of R and C, gives us units of time. Let's just play with units, right? And so problem 32. Right, so it will be very simple. 28, 32. All right, so we need to show that units of RC is actually second. Right. Okay, so so units of time it's units of RC. And so now let me write those units. You know what? I usually don't remember the relationship between units. It's too much to remember. I usually remember formulas, important fundamental formulas. And then by looking at the formula, you can immediately see the relationship between the units. So let me do the same here. I will open my explanation box. And so resistance. So again, I need to write in terms of something else. Right? So how did we introduce resistance? Just formula. You remember resistance was introduced a few classes ago as the potential difference divided by the current through the element. So delta V divided by I. So as a result, I can write so that ohm is related to the units of electric potential and current in this way. So I can write V divided by amp, right? So that's what I'm going to use over here instead of that R, right? And then in order to write units of capacitance farad in terms of something else, let me recall the definition of capacitance. And we define capacitance as this: charge divided by the potential difference Q over delta V. Of course, potential difference across a capacitor. So now it means that farad equals to coulombs divided by volts. Farad equals coulombs divided by volts. Okay, so now I can close my explanation box, and of course this goes instead of C. So now let me put them together. So it will be volts times divided by amps times coulombs divided by volts. So volts, of course, are cancelled, and we have coulombs over seconds. I mean, coulombs divided by amp. So now let me write current in terms of coulombs. In order to, how can we do that? Again, I usually recall definition of current, right? So definition of currents, it's a dq over dt. So it means that amps equals coulombs divided by seconds. So I can write amp equals coulombs divided by seconds. So that's what I'm going to use instead of my amp. Right. So finally, we're getting coulombs divided by seconds. Coulombs gets cancelled, and seconds, of course, jumps to the numerator. Right? You remember how to deal with fractions in the denominator. So seconds. Okay, so that's the proof that this unusual product of resistance and capacitance actually gives us a units of time. Completely unexpected.